Hello, my name is Anthony Reale, and I'd like to take you through the journey of my senior project, Strait Power. Simply put, Strait Power is a hydroelectric solution without the dam problem. It starts with my city, Detroit. Detroit has always had a large motor, the Detroit River. It produces approximately 370 million foot-pounds per second. Detroit earns its nickname from Motown music and the auto industry. Having the ability to redefine itself, Detroit can show the world how to empower its people carbon-free. My inspiration was a fish, the basking shark, a 22-foot-long, 5-foot-wide-mouthed giant that swims 18 hours a day with mouth open, sifting for food. I began to study the shark, hoping to learn from it. Water enters the mouth and exits through the gills. The lesson learned is that fluid movement is more than just using the energy flowing through you, but the energy flowing around you to aid in your task. Strait Power consists of two converging nozzles. Water enters the first nozzle by direction of the orange arrows. It's accelerated past two turbine blades. Upon exiting, the water receives energy boost, causing the water to flow more rapidly through the center nozzle. With an idea in mind, I approached DTE to find out how much energy was used and how much Strait Power had to produce. Contacting Great Lakes Observing Systems for information about current river speeds, I plotted a map of viable locations that Strait Power could function in. On June 30th, 2010, University of Michigan's Hydrolab described an open water blade system in development. They agreed to combine our projects and test Strait Power. Drawing inspiration from the shark, version 1 was a tribute to the gaping giant's mouth. With visualization of inspiration, I quickly moved on to version 2. With visions of water rushing through the turbine, I thought Strait Power should consist of an electrified grill for deflecting debris and diverting wildlife, a nose cone to help in accelerating the water past two turbine blades, with a planetary gear transmission and electric motor. Water rushes into the turbine, rotating the first turbine, then reverses direction when it hits the second. With the concept conceived, I approached University of Michigan with my idea for testing. With my idea approved, it was time to build a prototype. The prototype started with $0 and nowhere to build it. CCS was going through renovations. On August 1st, I had to find a workshop and funding. Testing was going to start at the end of October. I first found 3 trees to build Strait Power. Started working with a local lumber mill to turn the trees into lumber. But the mill informed me that the wood would not be ready until October. Then I traded my lumber for the use of some tools, which led me to Dennis Burke, a man who gave me a place to build Strait Power. So I put 1,000 feet of lumber on my credit card and began to build. It all started at Dennis Burke's woodshop, a place where 4,800 cuts would be made in 26 days. 8 rings were assembled, glued with every scrap of wood there was. Total, 390 hours before we made it to the CCS woodshop. Here is where we chainsawed, glued, doweled, and hammered the rings into workable, manageable shapes for the mill. Once the parts came off the mill, they were then sanded, finalized, shaped, trimmed, put into the perfect condition for assembly. All the joints had lined up, all the boards were in place, surfaces were flat. It was time to build the transmission. Transmission consisted of a custom gasket, some pinion gears, housed in an aluminum housing from a go-kart differential. These parts had to be remachined, milled, and put on the lathe so that they would work in the fashion that I wanted. Assembling them together, the transmission came to fruition. Assembly continued on the nozzle. Simple tasks like sanding the inside required the use of a jib crane donated by the school to get in and out of the model. Sanding every surface, I added another 3 gallons of body filler to smooth out all the contours. The seams were lining up, All the math I'd done was correct. The 4,800 boards really came together into one fluid, dynamic shape. All that was left was to finish sealing it with marine paint and assembly with a forklift. Adding a little bit of sealer to seal up all the holes, placing it down ever so carefully, and screwing it together. Strait Power was packed and ready to head off to U of M. 32 days of prepping and cutting. Another 256 hours went into Strait Power. On October 23, 2010, a truck from U of M's Hydro Lab came to pick up Strait Power. It was 711 hours of work. Strapping it down with tender loving care, hoping and praying that it would make the journey, I placed the transmission in the back of the truck. Ready for its long trip, I awaited its final assembly at U of M's laboratories. When it arrived at U of M, we had the task of placing it inside its mount. We had to build a custom aligning bench, assemble the transmission, weld the final drive shaft, and imagine the water flowing through it. Now time to tame the beast. University of Michigan's Hydrodynamic Lab, home of the largest educational tow tank in the U.S. This is a place where they test military subs, America's Cup boats, and Discovery Channel shows. With testing about to commence, a redesign was in order. We used a load cell to capture drag data, a hydraulic pump and pressure gauge to capture energy produced. What do you do with 1 million gallons of water? Well, you add 1.5 feet to it if you're going to test Strait Power. Testing Strait Power was more than just throwing it in the water. This was a 900-pound model made of wood, steel, aluminum that had to be placed in. The problem with wood is that it likes to float. So once we got Strait Power into the water, we had to add 600 pounds of lead weight to it to sink it just enough to fit under the carriage. Then pulled into place by the straps, 900 pounds of force was taken to hold it down. Trying to burst from the water, our clamps and metal held it in place for its first inaugural run. And then it came. Strait Power started to make electricity, producing pressure. The oil from the pump started running freely. As with any testing, we were stressing the limits of possibility. From all this testing, Strait Power started to crack and swell, wanting to burst from the water from its buoyancy force. It grew another 4 inches, but we continued to test as it was holding together. And then, nothing. We had to send in the robot to find out what was wrong. Knowing something was broken, I jumped in, took it apart underwater, brought it out, and found that a weld had broken off on our pinion gear. With it reassembled, we were back to testing. We added a new hydraulic pump, and we could begin seeing the water flow. Until part of the shaft broke again. This time, the blade had spun and stuck on permanently. Disassembling Strait Power, rebuilding the center shaft, we were back to testing. With another hydraulic pump in place, we were able to dial down the pressure and really create some power. Strait Power is more than a possibility. It was time to go home. It was time to release Strait Power for from its underwater prison, to bring it back to the surface, to see what it had done, to see what it had become. A cracked, swollen beast of a project. With signs of aging, rust was forming, emerging everywhere. It was removed with the utmost care. It still had its own force to rise to the surface. Putting on an extra 300 pounds of water weight, Strait Power came out a swollen, cracked giant. It was time to do what we had to do to characterize the system, to see what kind of forces and energies were lost. So we reassembled the transmission, put the fan blades back on, and designed a fixture for testing. The fixture consisted of a 1-to-7 gear reducer connected to 2 pillow block bearings that supported an electrical motor about the axis of rotation with a 1-foot arm. So we could measure foot-pounds of force produced. By knowing the RPM speed, we were able to calculate energy lost in the system. It was time to remove Strait Power. It was time to take it home. It was the middle of November, and 200 more hours had been put into the project for testing. A total of 911 hours to make Strait Power. Donations from the University of Michigan were $80,000 for testing and parts. Private donors, anonymous donors, and CCS donated $15,000 in milling machine time to produce Strait Power. $95,000 later, my dream, my vision, had come to fruition. Strait Power version 1 improves power output of a single turbine blade by 40%. I next drew a visual interpretation of the water flowing around Strait Power, which led me to lengthen the 2 nozzles to decrease the pressure wave produced by Strait Power. With a good grasp on the idea, it was time to apply Strait Power's concept for the world. Concept 1 for outdoor enthusiasts and the military. This consists of a portable, collapsible version which expands when cast into a moving body of water. It can then be used to remotely power electrical devices, such as GPSs and fare fences. The next application is for industrial use, producing a minimum of 40,000 watts. This megamouth design has a 10-foot diameter blade, allowing wildlife to pass freely through it. The next version is for the residential market, able to be placed under docks or on riverbeds. It consists of a removable powertrain system that can run hydraulic or electric motors. This allows the user to run electric devices or hydraulic equipment, such as presses and log splitters. Operation Red Remote Location, Emergency Relief, and Developing Nation provides systems for deploying power stations along the river's edge. Now back to Detroit. Deploying a combination of barges, megamouth designs, Strait Power could produce the energy the city needs, 100% carbon-free. Barges are inexpensive to build, easy to service, and can be used as wildlife refuge for migratory birds. Strait Power is a choice on living better. I'm Anthony Reale, and I'd like to thank you for listening.